the Gauss law for magnetic flux. Just like how we said that the Gauss law for electric flux, this guy is equal to the total charge enclosed. We had it that d dot ds over a closed surface is going to be equal to the charge enclosed by that surface. Yeah, the same concept here. Gauss law for magnetic flux tells you is that whenever I have a closed surface, if I take the net outgoing flux, which is what this guy means, net outgoing, yeah, it's not incoming. Incoming is negative of outgoing, yeah. Net outgoing flux is equal to 0. And this is always 0 for the magnetic case. The reason being, for magnetic field, for magnetic sources, we don't have monopoles. We always have dipoles. It's only in the electric field, right? I can individually enclose one charge. I can say that it is enclosing a charge of, let's say, minus q here, because all the flux lines are going in. Whereas in the case of magnetic field, since there is a south pole that I enclose, but there's always a north pole next to a south pole. Even if I draw the surface in between the north and the south, what I will have is incoming flux in this area, but inside the bar magnet, the flux is from the south to the north. So what is coming in cancels off what goes out, and the net flux that cuts through is going to be equal to 0, because magnetic monopoles don't exist because of the magnetic dipoles. Or what are the fundamental source of magnetic field? They are not monopoles. You don't have any north pole or a south pole separated out. So that's an interesting observation here. So similar to the electric flux case, you can have, instead of integral, this is the integral form, you can have it in the differential form as well, which is gradient of B is equal to 0, or divergence of B, sorry, divergence of B is equal to 0 all the time. Yeah, it's not equal to charge enclosed, because there is no, unlike the electric field case, there is no separate magnetic monopole charges. It's always dipole. The north and the south cancel each other, so it's always 0.